Welcome back, everyone. We're going to talk about the equipartition principle or equipartition theorem. This is chapter 3.2 in your textbook, and this is about the end of the statistical mechanics that we are going to cover this semester. From here, we're going to start talking more about collisions and reactions and start talking about how we put these ideas that we've been thinking about for single molecule systems into more complex things and move into being able to do some actual chemistry. Okay, so we keep coming back to temperature. Temperature is super important. And today we're going to really try to understand how temperature and energy levels really interact with some beautiful approximations. So the population of the energy levels, so that this means the percentage of the number of molecules in a system occupying any particular energy is dependent upon the temperature. And the temperature is defined as this partial derivative that we have seen several times. Now, to try to make a simpler, easier to use link, we're going to work to define the energy that is contained within the molecules in terms of kBT. Okay? Okay, so we use kBT for molecule level energy explanations. What does this mean? Okay, well, the units of the Boltzmann's constant times temperature are joules or wave numbers or other unit of energy, because remember that kB has units of joules per Kelvin, and then we multiply it by temperature, giving kBT to have units of energy. This is energy per molecule. But the ideal gas constant is defined as Avogadro's number. So this is Avogadro's number, 6.022 times 10 to the 23 inverse moles, times the Boltzmann's constant. And so we can also express our energy per mole in terms of the ideal gas constant times temperature. So in this, R has units of joules per Kelvin times mole. And if we multiply this by temperature in Kelvin, it gives us units of joules per mole. And so we use RT in our expressions whenever we are thinking about mole level things. This is why in homework 1, we were able to write the Boltzmann distribution both in terms of the Boltzmann's constant and in terms of the ideal gas constant. It just depended on what our perspective was. Were we counting molecules or were we counting moles? Okay, so let's start with translational energy. This is something that we actually haven't talked a lot about because it turns out that the partition function for translational energy is incredibly complicated. And so we aren't going there. But what we can do is we can use the Boltzmann's distribution to be able to figure out the average kinetic energy in a system along one dimension. So let's start with the x direction. Because kinetic energy is not a quantized energy, remember, you can go any speed that you want in your car, we can get the average value of this energy using the classical average value theorem, which is taking this energy, this is our kinetic energy, times the probability, and integrating over all space. If we do this, your book does it for you. I don't really care that you can. If you do this, we get that the average energy in the x direction is equal to 1/2 kb times the temperature. This is a very simple answer. We like simple. Now, that was just thinking about translations in one direction. If we allow our molecules to move in 3 directions, we find that each direction contributes 1/2 kBt to the energy. And so this allows us to think about our E translational is going to be equal to our average energy of our x direction plus our average energy of our y direction plus our average energy of the z direction, giving us 3/2 kBt. This 3 directions is what we call 3 degrees of freedom. And we're going to continue seeing what we mean by degrees of freedom. Okay, so if we think about this in terms of rotations, in addition to translations, it turns out that we can use the same average value theorem for rotational and vibrational energy. And we're going to talk about vibrations in a minute, but to start with rotations, if we solve this out, we determine that the average rotational energy for each type of rotation is 1/2 kBt. And then the question becomes, how many directions can a molecule rotate? And that depends on the shape of the molecule. So diatomic molecules can rotate in 2 directions. And each direction contributes 1/2 kBt. And so we say that there are 2 degrees of freedom. And so we have 2 times 1/2 kBt, giving us a contribution of kBt for that. Nonlinear triatomics have a 3rd direction that they can rotate. So remember, whenever we talked about the rotational partition function, that for these linear molecules, that rotation along this axis of the bond, that spinning, did not count as an actual rotation because there was no change in the positioning of the atoms. But when we look at a nonlinear triatomic, that motion is going to contribute to the rotational energy. And so for nonlinears, our rotational motions can donate 3/2 kVt. I'm going to put this information in a table to summarize it all at the end. Okay, so vibrations are a little bit strange because vibrational energy in molecules have both a kinetic and a potential component. There's the kinetic energy of the movement of the spring, and there's the potential energy of the strength of that spring. And we can solve the average value theorem for vibrational energy the same way we did for translational and rotational. And we find that for each form of motion, we get 1/2 kVt. But we have to think about how each vibrational mode is going to provide 2 units of energy. So we have this kinetic component and this potential component. And so the average energy from vibration becomes kBT. So the equipartition theorem just tries to put this all together. And it says that the energy of our molecule is going to be equal to this 1/2 kBt times the number of molecules in our sample times our in equipartition. And this is our total degrees of freedom. And if we wanted to put this in terms of moles, we can. We just have to use R and N for our number of moles. This is a way of approximating the energy contained within a system of molecules, in number of molecules, at a given temperature. Okay, so this in equipartition is really a count of the degrees of freedom. And so to do that, we have to know the shape of our molecule. And each degree of freedom is going to donate 1/2 kBt to the overall energy. All molecules donate 3 degrees of freedom for translational motion. So they can go X, Y, and Z directions. Monatomic molecules do not rotate. This would be something like the helium atom. There's no rotation. We can't spin it and move the positioning of the atoms. Like we talked about before, diatomic and linear triatomic, they have 2 directions of rotation, and nonlinear triatomics have 3. Our vibrational modes Our vibrational modes actually have a formula that we can use. So if the molecule is linear, there are 3n, which is this is the number of atoms, minus 5. If it is nonlinear, there are 3n, also our number of atoms, minus 6 degrees of freedom, DOF. So to get our total, and hold on, back up. So remember that this times 2 is for our kinetic and potential energy. To get our total, we're going to take our 1/2 kBt times the sum of our degrees of freedom for each type of motion, and it is going to be equal to this total energy expression. Well, so remember in homework 2 how you started finding that in order to get molecules into this excited vibrational state, that you had to increase the temperature a lot. These spacings of between vibrational levels are usually greater than 1,000 Kelvin. Not 100, 1,000. And so that means that at room temperature, for most molecules, vibrational levels do not really contribute to the overall energy. And electronic levels are even bigger. And so electronic levels really don't contribute to that energy. And so that means that most of the important degrees of freedom are going to be rotational and translational. Now, there are exceptions to this. Remember, we talked about torsional motion in proteins in homework 1, where that vibrational mode of torsion was important. But for the most part, for most motions, most of the molecules in our system demonstrate that increase of energy with temperature as rotational and translational motion. Okay, so now try this. From the equipartition theorem, which is our E total is equal to 1/2 kBt times our number of molecules times our number of degrees of freedom. Estimate the energies in joules that must, joules, that must be removed to cool 1/2 mole of helium gas and 1/2 mole of carbon monoxide gas by 100 Kelvin, from 1,000 to 900. And you can assume that nothing else is changing with the system besides the temperature, which is important for thinking about this. And remember that we can also write the equipartition theorem in terms of moles and are. Okay, so this finishes up chapter 3. From here, we are going to skip chapter 4, and we're going to start talking about some of the material in chapter 5.